the position of equilibrium, we've been working on identifying, knowing what side of the reaction is favored, looking at acid-base reactions. And we've been using pKa to determine which side is favored, but we also have to know what the acid is on each side. There should be an acid in the reactants and an acid in the product. And for me, my most simple method of identifying the acid is to compare the reactant and the product to determine which molecules have one more hydrogen than the other. So if you first identify the molecules that only differ by one hydrogen, then looking at those two, you can label one, the one that has one more hydrogen than the other, as the acid, and the other, which has one less hydrogen, as the base. Once you've identified one set, you can automatically label the other molecule in the reactant or the product as the opposite of the molecule that it is with. But you can also use the same methodology. They differ by one hydrogen, and we can label the one with an additional hydrogen as the acid, which in this case would be ammonium ion, and the other, the ammonia, as the base. Once you know which of the two are which in the reactant is an acid and which in the product is an acid, then you look up or pull from your memory the pKa, knowing that carboxylic acid has a pKa of about 4 to 5, and a protonated amine, like ammonium ion, has a pKa of about 10 to 11, then the higher pKa acid is the ammonium ion, and the equilibrium should favor formation of the ammonium ion. And we can see how the book answers this question by looking at this arrow, which confirms that formation of the ammonium ion is favored. Looking at the bottom, we can first compare the two most similar, though differ only by one hydrogen. The CH3CH2OH has one more hydrogen than CH3CH2O, and so it is the acid. And the CH3CH2O- is the base. Since you have to have both an acid and a base in the reactants, if the alcohol, the CH3CH2OH, is the acid, then the CH3NH2 has to be the base. And in the products, if the CH3CH2O- is the base, then the CH3NH3+ has to be the acid. Now that you've identified both acids, you compare their pKa's by either having memorized the pKa or looking it up. Then the pKa of the alcohol is about 16, and the pKa of the protonated amine is 11. 16 is greater than 11, so the formation of reactants in this case is favored. We can calculate equilibrium constants using the Henderson-Hasselbalch equation, and also by remembering what our pKa's are. I will not ask you to calculate equilibrium constants. I will ask you to compare pKa's, and I will ask you to determine which side of the reaction is favored at equilibrium. But reviewing calculation of equilibrium constants from pKa, if we subtract the pKa, if we take the pKa of the reactant acid minus the pKa of the product acid, we can find pKeq, and then the negative log of pKeq will give us the Keq. And if you remember so pKeq is the negative log of Keq, and so the anti-log of Keq is to raise both sides to the power of 10. So, for example, if pKeq, or the negative log of Keq, is equal to negative 4.6, and I raise the negative log of Keq to the power of 10, because you have to do in algebra, whatever you do to one side, you have to do to the other. Raising a log to the power of 10 cancels it. So that log to the power of 10 is, well, actually, we should transfer the negative charge to the other side before we raise it to the power of 10. So I will just erase that. And if I transfer the negative charge from log Keq to the other side, and I have a negative 4.6 divided by a negative 1, that will give me a positive 4.6. So that if we raise both sides to the power of 10, the log of the 10 to the power of log Keq is equal to Keq, and that cancels the log, and then that will equal to 10 to the 4.6. And you solve for Keq. Since you're not going to have to do this calculation on an exam or in the ACS test, we're going to move forward. Okay, the strength of an acid is determined by the stability of its conjugate base. We can rate acid strength with pKa, and we can rate the conjugate base by pKa. We can rank how stable the conjugate base is based on the pKa as well. So the more stable the conjugate base, the stronger the acid. And this is a rule that we've covered a lot. What we actually typically say, and what I've always hear students repeating back to me, the stronger the acid, the weaker the base. Well, the statement that they've written here is essentially to say the stronger the base, or the weaker the base, the stronger the acid. So a stable base is a weak base. Or non-reactive. So when we say a molecule is stable, it is less reactive. Which would mean that it would be less capable of donating its electrons. And so we can say the stronger the conjugate acid, the weaker its conjugate base. And we have to rank molecules according to their relative acidities. And we can do this using pKa, but we're also going to learn some of the periodic trends that can help. But our periodic trends in this case are limited because you can only compare down a group or across a row. It's not usually valid to do both at the same time. So for example, you shouldn't compare phosphorus in row 3, group 5, to oxygen, which is in row 2, group 6. You should not compare things that change in both group number and row number on the periodic table when we're talking about acid and base strength. Okay, relative acidities. And this is the relative acidity of a proton. Okay, so we're talking about a proton bonded to carbon versus a proton bonded to nitrogen a proton bonded to oxygen versus a proton bonded to fluorine. I'll write it above there. Okay, HF. So what you might notice is that we have carbon group 4, nitrogen group 5, oxygen group 6, fluorine group 7. So we're comparing across a row, and as we go across a row, the acid with the lowest pKa is HF, which has a pKa of around 3, I believe. Then we have water, which has a pKa of 16. Ammonia, which has a pKa of about 35 to 40. And then a alkane, which has a pKa of greater than 60. And as we go towards the more electronegative atom bonded to hydrogen, fluorine, as we go towards fluorine, the pKa is decreasing and we are increasing in acidity. If we look at the conjugate bases of these acids, where each of these acids loses the proton that's already given below, we have a deprotonated methyl group, amide ion, hydroxide ion, and fluoride ion. And so the rule of stronger acid, weaker base is applied, and then we can say that fluoride is the weakest base, and that CH3 minus is the strongest base. And in my experience on the ACS test, the language that they use is not which is the most stable base. What they typically act is which is the weakest or which is the strongest base. And so that's the terminology that I'm going to focus on when I ask questions on an exam. Since we're not talking about PKBs at all, we're only going to deal with PKAs. If you're asked to compare base strength, you either have to know the periodic trend or you have to be able to think through the process of taking the base, converting it to its conjugate acid, and looking at which is the strongest acid to determine which is the weakest base. So let me write that out on the side. Take the base, draw the conjugate acid, rank the acid, the strongest acid corresponds to the weakest base. It's not going to work. There's just not enough room. Okay. Strongest acid indicates conjugate base that is weakest. Okay. Hopefully that is clear to you.